Okay, so I'm going to have a look at question 9 in the Leaving Certificate Higher Level Maths Paper 1 for 2018. So we have a diagram here, and it shows the first 4 steps of an infinite pattern which creates the Sierpinski triangle. The sequence begins with a black triangle. It's equilateral. Each step is formed by removing an equilateral triangle from the center of each black triangle in the previous step as shown. Each equilateral triangle that is removed is formed by joining the midpoint of the sides of the black triangle from the previous step. So this point here is the midpoint of this side here. Similarly with these two here, they're the midpoints. This point here would be the midpoint of this distance here, and so on. Okay, so the first thing we've got to do is, let's see, the table below shows the number of black triangles at each of the first 4 steps and the fraction of the original triangle remaining at each step. We've got to complete this table. So at step 0 we have the number of black triangles. We have 1 black triangle. So the fraction of the original triangle remaining is 1 over 1 if you like. Now at step 1 here, we've removed this triangle here, so we've got these 3 black triangles. So in total we've got 4 areas, 1, 2, 3, 4, 4 equal areas. We've removed one of the areas, so we have 3/4 left. So the number of black triangles we have would be 3. I'll just do that in black here, so this is 3, and the fraction of the original triangle remaining then would just be 3/4, 3 over 4. The number of black triangles then in step 2, well, we can just count them, but 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 triangles, and the fraction of the original triangle is going to be 9 over 16. We've got a total of 16 areas. And we have 9 black triangles, so that's 9 out of 16. Similarly here, you can probably spot the pattern at this stage, but we are multiplying each of the number of black triangles by 3, so we've got 27 black triangles here, so it's going to be 27 out of, and you can probably see the pattern on the bottom here as well. We are multiplying by 4 each time here, so we have, you can count them either, total number of 64 areas here, and we have 27 black triangles. So that's it. Let's just have a look at part B1. Write an expression in terms of n for the number of black triangles in step n of the pattern. The number of black triangles. Well, what we're doing here, you can probably spot the pattern here anyway. We're taking 3 and raising it to the power of the step, if you like. So it's really just 3 to the power of n. So for example, the number of black triangles in step 0 is 3 to the power of 0, which is 1. The number of black triangles in step 1 is 3 to the power of 1, which is 3. 3 to the power of 2, 9. 3 to the power of 3, 27. So this is our expression in terms of n for the number of black triangles. So this is the number of black triangles in step n. Okay, so step K is the first step of the pattern in which the number of black triangles exceeds 1,000 million, or 1 by 10 to the power of 9 for the first time, and we've got to find this value of K. So we know that 3 to the power of n. 3 to the power of n is our number, is the number of black triangles. So step K then is the first step in the pattern in which the number of black triangles exceeds 1,000 million. In other words, 3 to the power of k, n is the number of steps, so we have k steps, is not equal to, we want it to be exceeds 1,000 million, so we want it to be greater than 1 by 10 to the power of 9. So really we've got to work out what this k would be then, what this n would be, or what this k would be, in order for a number of black triangles to exceed this amount here. So when you see this kind of thing here where you've got your variable as the power, usually what we have to do here is just take the log of both sides. So I'm going to take the natural log 3 to the power of k greater than the natural log here of 1 by 10 to the power of 9. So we'll just use our law of indices here, take the k here and bring it down, take the power, bring it down in front here. So you got k times log 3 greater than log 1 by 10 to the power of 9. Now we can just get k on its own here. This k is multiplied, so I'm going to divide across by log 3. So really what we end up here is with log 1 by 10 to the power of 9 divided by log 3. So what we end up with then, you can just do this, these are all just numbers, you can work these out on your calculator. We get n is greater than 18.86, or k rather is greater than 18.86. So our answer here then is just 19. So you can check that. I mean, if you take 3 to the power of n, you can take 3 to the power of 18, for example, and you can do that on your calculator. You'll get 3.87 by 10 to the power of 8. Now that's less than this here, less than 1 by 10 to the power of 9. If you do 3 to the power of 19, on the other hand, you get 1.16 by 10 to the power of 9. So we do get a number here. When we go to 19, when our k here is 19, we do get a number greater than 1 by 10 to the power of 9. We get 1.16 by 10 to the power of 9. Okay, so let's move on. Let's just have a look at C part 1. So let's see, we've got step H is the first step in the pattern in which the fraction of the original triangle remaining is less than 1 over 100 of the original triangle. Find the value of H. So what we're going to do here is just look at the fractions, the fraction of the original triangles remaining, and we have that in our original table here. We're going to look at this kind of sequence of numbers here. So I'll just write these down here. So we have I'll write the steps here, step, and the fraction remaining here. So we have step 0, we have step 1, we have step 2, we have step 3. Step 0, well, the fraction remaining was just 1 over 1, if you like. Now there was 3/4 remaining after step 1. There was 9 over 16 remaining here, 27 over 64 here. So there are a couple of ways of looking at this, but you can look at this really as a geometric sequence of numbers here, where you're multiplying each term by 3/4. So if we take this here as, let's say we'll take this as T1 because this is step 1 here, this is T2 here because this is step 2, this is term number 3 here because this is step number 3 here. We can look at this as a geometric sequence of numbers where A here is equal to 3/4 and OR here is also equal to 3/4. So really, if we want to read the question again, it just says step H is the first step of the pattern in which the fraction of the original triangle remaining is less than 1 over 100. So we want less than 1 over 100 somewhere out here, and we want to know what that which step that is, which n it is, if you like. So if we take for example Tn, Tn is going to be A times OR to the power of n minus 1. Now A OR to the power of n minus 1, our A is 3/4, the OR is 3/4, and we want, we have an n minus 1 up here. We want this to be less than 1 over 100. So what we've got to do here is really just work out what this n is, the step number. This is our value for h, if you like. So let's just work this out. First thing I'm going to do is just divide across by 3/4. So if we divide across by 3/4, we'll end up with 3 over 4 to the power of n minus 1 on this side, and on this side here we'll end up with 4 over 300. Divide 1 over 100, in other words multiply by 4 over 3 if you like. Dividing by 3 over 4 is the same as multiplying by 3 over 4. Sorry, 4 over 3 I should say. Multiply the top by 4, the bottom by 3. Okay, so now at this stage we have our power here. The variable is in the power here, so we need to just get the log of both sides. So I'm going to get the log of 3 over 4 to the power of n minus 1, and also the log of this side as well, 4 over 300. Next step then is bring this power down here again, so I'm just going to take the n minus 1 here, multiply it by log 3 over 4. Okay, and now all I've got to do is divide across by log 3/4. Now just be a little bit careful here. Log of 3/4 is actually a negative number, so you've got to switch this around here. So we end up with log 4 over 300 on this side. We got to divide by log 3 over 4 on this side, and then we just simply add 1. So n then is going to be greater than log 4 over 300 divided by log 3 over 4, all plus 1. Okay, so finally got there. So what we end up with there is n is greater than, the bottom here we just end up with n here is going to be greater than, when you work all of this out, it's all just calculator work, you get n greater than 16.0078 and so on. So in other words, n has to be equal to 17. Now that's kind of a long-winded way of doing it, but that's one way of doing it. But you may have noticed as well that this here, we have a 3/4 here, we have a 3/4 here. So this is actually 3/4 to the power of 1. So we multiply these two together, we just end up with, we add the powers here, we just end up with 3 over 4 to the power of n. This is just 3, all of this is just 3/4 to the power of n when we add the powers, less than 1 over 100. So it may just be a little bit easier by just again taking the log of both sides, so you get n log 3/4 less than log 100, and so on and so on and so on. You'll get the same number at the very end. Okay, so let's have a look at part 2 here. Now part 2 here, oh by the way, again you can check this, I should say, you can put in 3/4 to the power of 16, put in 3/4 to the power of 17, and you'll find that if you have 3/4 to the power of 16, you'll actually get 0.01002, and if you have 3/4 to the power of 17, you get 0.007516. So here you can see it's actually the first step is at 17 step, and here it is less than 1 over 100. Okay, so let's again have a look at part 2. So what fraction of the original triangle remains after an infinite number of steps of the pattern? Now, really this is just 3/4 to the power of n, where n goes to infinity. Now if you have a fraction and you multiply it by itself, you'll get a smaller fraction. If you multiply it by that fraction again and again and again, the fraction gets smaller and smaller and smaller. So in other words, if we take 3 over 4 and we raise it to infinity, which is not a number, by the way, it's just an idea or a concept, if you like. So if we take, in other words, if you like, the limit of 3 over 4 to the power of n as n goes to infinity, really what we're going to get here is 0. So the fraction, I guess you can write it as 0 over 1. If they're asking for a fraction here, you may be able to write 3 over 4 to power infinity, something like that. But this is the fraction. There'll be nothing of the actual. There'll be no area left within the original triangle, if you like, which is hard to imagine, but that's what would actually happen. Okay, let's have a look at part D and part 1 of part D. Now the side lengths, on the other hand, of the triangle in step 0 is 1 unit. So the triangle then is just, we're going to have our equilateral triangle, and it's going to be 1, 1, and 1. Now the table below shows the total perimeter of all the black triangles in each of the first 5 steps. Complete this table. So we can see here that the perimeter here is just going to be 1 plus 1 plus 1, which is 3. Now if we were to take triangle here, where we're dividing these sides in half, in other words, this is a half here, this is a half, 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 all these side lengths are a half. What's the new perimeter? Remember, this is our black triangle here, here, and here. This is white inside here, or blank if you like. So we'll have 1, 2, 3 here, we'll have a half here, and a half here, which is 1.5. So we'll have 3 plus 1.5, or just 4.5. So 4.5, we'll say, we'll leave it as a fraction, 9 over 2. Here we've got 27 over 4. Now if you go to step 3 here, you can probably see the pattern. What we're actually doing here is multiplying by 3 over 2. This is 3 over 1 here. We're multiplying the top by 3 each time, and we're multiplying the bottom by 2 each time. So if you take this here, we have 27 over 4. So the next one will be 81 over 8. The next one then will just be 243 over 16. Now you can just work this one out from the triangle above that you're given in the question, but I wouldn't go about drawing the 4 triangles, it's just going to take too long. From here you should really be able to work out the common ratio, if you like, of this sequence of numbers, or what we're multiplying by each to get the next one. Now let's have a look here. We have to find the total perimeter of the black triangles in step 35 of the pattern. Give your answer correct to the nearest unit. Okay, so we've got to find the total perimeter. So I wouldn't go trying to work this out for each step. There is a method for doing it that would be a little bit quicker. So let's have a look at that. We want, again, we have a geometric sequence here where OR is 3 over 2. We're multiplying each term by 3 over 2. So if we take, again, because the number 1 here is the first step, I'm going to take this as T1. I'm going to take this one as term number 2, this one as term number 3, and this is term number 4, and so on, because the ends here match with the step numbers as well. And we want T35. We want step 35, which will match with my T number, if you like, my term number. So again, we have Tn is equal to A or to the power of n minus 1. Now, in our particular case, starting here, our A here is 9 over 2, and our common ratio then is just going to be 3 over 2. So let's just work this out. We want to find, what do we have to find here? Step 35. So we want T35. We actually want T35, and we want the number of, or the total perimeter, actually, the total perimeter in step number 35. It's going to be quite a big number. You can see the numbers are actually increasing here as we go along. So our A is 9 over 2. Our OR is 3 over 2. We've got to raise it to the power of n minus 1, 35 minus 1, which is 34. Okay, if you do that, again, it's just calculator work here. You should be able to do that. Okay, you get 4, 3, 6, 8, 3, 2, 9. 4, 3, 6, 8, 3, 2, 9. So that would be units, whatever units we're talking about. Now you can see that's quite a big number, and we've only gone up as far as step number 39. So we started with a perimeter of 3, then 4.5, and so on, and it got bigger and bigger and bigger, and by the time we got to step number 35, the perimeter here is 4,368,329. So despite the fact that the area seems to be disappearing, the area reduces to 0, the perimeter seems to be just getting bigger and bigger and bigger, and if you go into infinity, in fact, the perimeter of the black triangles will in fact go to infinity. So let's have a look at the next question. This is to the nearest unit, by the way. There are decimals with this, but this is to the nearest unit. Okay, so here we have, let's see, part 3. We have to use your answer from part C 2 and part D2, which we've just done, to comment on the total area and the total perimeter of the black triangles in step n of the pattern as n tends towards infinity. Well, we had 3/4 to the power of n, and if you find the limit of this as n goes to infinity, well, that will just give us 0. A fraction multiplied by a proper fraction, if you like, multiplied by itself, as I say, will give you a smaller fraction, like a half times a half is a quarter, times another half is a 1/8, which is equal to 1/16 to 1/32, and so on and so on. It gets smaller and smaller and smaller. 3/4 to the power of infinity, if you like, will just tend towards 0. So the area will tend towards 0 as n tends to infinity. Now, looking at part D2, which is this part here, what we've got here is 9 over 2. We have our first term here, which is 9 over 2, and then we have 3 over 2, which is an improper fraction, a top-heavy fraction here, to the power of n. Now, if you take the limit here, the limit of 3 over 2 to the power of n as n tends towards infinity, this will tend towards infinity itself. This will go towards infinity because this is a number greater than 1. So 1.5 times 1.5, 1.5 times 1.5 is 2.25, times 1.5 is 3.375. So it just gets bigger and bigger and bigger, and as n gets bigger and bigger and bigger, this number here is going to get bigger and bigger and bigger, and so the perimeter of the black triangles will just tend towards infinity. So we can say something similar here. We can say that the perimeter of the black triangles tend to infinity as n tends to infinity. And that's really it. So it's an odd kind of concept here. Despite the fact that the area tends to 0, the actual perimeter of the black triangles will tend towards infinity. Okay, so that's it for this particular question.